Hi, this is Andrew sir from Judbir Higher Secondary School, Gurubathan. I'm going to do physics with you, and I'm starting right from the first chapter. Usually I start light. In all my career I have done that one here in Judbir. But then I'm going to, as I was asked to do this, so I'll start from electrostatics. Okay. Today what I'm trying to do here is, since we have very limited time frame, and then once this video goes it has to be I think we'll have to wait for next week for this to come. So possibly what I will try here is finish nearly about first and the second chapter, otherwise half of the second chapter. So in the first chapter we almost have the introductory part of electrostatics. Let me bring you idea of electrostatics. Statics here means rest. Well, the other part of it is dynamics, we know. So when I'm talking about electricity, current electricity, so that comes in the dynamic electricity part. Whereas the electrostatic, it deals with charges at rest. Now, let me bring you the idea of charge, okay? Electrons are mostly responsible for the charge in a particular body. So basically when I talk about electrons, there is a topic called quantization of charge. Now what do you mean by quantization of charge? Let's see this. Now we all know the charge of an electron is 1.6 into 10 to the power of minus 19 in Coulomb. Coulomb happens to be the SI unit of electric charge. E equals to 1.6 into 10 to the power minus 19 Coulomb. Now this is very interesting fact about the charge of an electron. So what is interesting about this? Let's see this. Whenever a body gets charged, it means the body will be charged only in an exact multiple of the charge of an electron. This is so interesting fact. This is the concept of quantization. Now let me bring you the concept of quantization. What is quantization? Where did the word quantum or quantization came from? It originated from Max Planck. Max Planck started this. He was working on radiation, and when he was working on radiation, he found out that the radiation energy emitted was in the packets. Alright, it was not a continuous form, but it was in some packet form. That's like particle type, hi-fi. Okay, so in the packets, exactly, and that tiny packet of energy was termed as quanta by Max Planck. It was coined by Max Planck, and later on Einstein actually proposed that for dual nature of light, later on otherwise quantum theory of light, and then he said that particular term as photon. That packet of light, that packet of energy of light was termed as photon by Einstein. Exactly in the similar manner here in static electricity, when I'm talking about quantization of charge, it means charges, when it is given out or absorbed by a body, let's say, then it is done in an exact integral multiple of the charge of an electron. So this charge is very interesting. So it means if the body loses electron, it will have to be in an integral multiple. It means the whole number multiple, not exactly like fractional type. Okay, say 10 electrons, 20 times E, 30 times E, 1000 times E, 10,000 times E, and so on and on. That's the idea. All right. Now this electron has another special quality. If I go down and when I finish the chapter electromagnetism later on by your teachers, and then you will find that in the topic chapter called magnetic properties of matter, there you will see something called as a Bohr Magneton. It means the dipole moment, magnetic moment associated with tiny particles. And if you see, Bohr Magneton was termed on the basis of the magnetic moment associated with the spin of an electron, and that is not only that, but it was also found to be equal to the magnetic moment associated with the orbital motion of the electron in an hydrogen atom. That was Bohr Magneton, and this Bohr Magneton has a value of, if you see, it is 9.274 into 10 to the power minus 24 in ampere meter square. That is your MB called as a Bohr Magneton. Now this one is also interesting. This is the magnetic moment associated with electron, and this is the smallest quantity of magnetic moment present in any matter particle. There is nothing smaller than this. So electron has two striking features. One, the charge of an electron. Another one, the magnetic moment associated with the electron, the spin of the electron, otherwise the orbital motion of an electron, and that is this. Well, the concept of quantization, hopefully it is clear to you. Well, I'll go to the next section of it. What do you mean by the body is charged? See, basically a body cannot be entirely positively charged or entirely negatively charged. What I mean to say is, if I say the body is negatively charged, it don't mean that the body has only negative charges in it. We all know any matter particle comprises of atom. An atom, if you go to the structure of an atom, then we see inside the nucleus of an atom we have positive charges called protons, and outside that, surrounding it, according to the Bohr's concept of the structure of an atom, we have electrons revolving around it, and these are the negatively charged particles. Okay, let me cut short this particular point and divert your attention to the idea of what do you mean by positive and the negative charges. Now, negative charges does not mean less or small quantity of charge compared to the positive. Only the convention was given as if there are two different kind of charges. So if one kind is given as a positive charge, exactly the replica of the other one is taken as the negative charges. That's it. Otherwise, if you look at the positive charge and the negative charge, say the charge of a proton or a charge of an electron, if you go and have a see it, then the charge of a proton is exactly equal to the charge of an electron if I see it. All right? Okay. Well, now let's focus to the idea of how electrical, I was talking about atoms, and I was saying that no body is strictly positively charged or strictly negative charged. What do I mean by that one? Let's see. Say a body is comprising of atoms, as I already told you. So it has positive charges inside the nucleus. So there is no way I can bring out those positive charges from the atom. It is still there in the matter. So what I can only do here is whether I can remove the electrons from it or otherwise add some more electron in that particular body. So when I remove the electrons from it, then the number of negative charges are smaller compared to the positive charges inside the atom. That's the reason why then the body will be positively charged in, precise sense, I would say net positive charge to be more better. Whereas on the other hand, so when the body has some more electrons absorbed by it, otherwise if the body acquires some more electrons, then the net negative charge in the body becomes more compared to the positive charge, and then the body becomes negatively charged. That's it. Okay. Now how are bodies charged? Like how do they become electrically charged bodies? Okay. Basic idea about the bodies being charged is, number one, it's the method of friction, which I've already learned that in class 8, I hope. Well, friction will cause the charge separation, and obviously it is the electrons which plays the role here, because you cannot move a proton which is deep inside the nucleus. So what actually electrons do? Electrons separates out and the protons remain there. So one of the body will have more number of electrons, where the other body will have less number of electrons, meaning it is positively charged. The first body which will acquire electrons in it will be negatively charged. That's the idea. There is another way of making a body charged, and there is, but for this purpose I will need a charged body. This mechanism is called induction. Now what is induction? Let's see. Say if I bring a charged body, let's say this is a positively charged body, and if I have a conductor here. So induction, basically I'll have to talk about induction in two different formats. One is in case of a conductor, another one in case of an insulator. Otherwise I would more say that one as a dielectric. But as substances, depending upon the nature, electrical nature of the substance, I can actually categorize substances into three categories. Number one is called a conductor, where we have, like maximum number of free electrons in it, and the electrons are responsible. The second one we call as a semiconductor, where we have these electrons and the holes, which are actually the charge conductors. And the third one we have is an insulator, where we do not have any free electrons for the conduction of electricity. Well, we will talk about this one more when we go to the chapter of electronics. There we talk about band theory of solids, and there why insulators do not have free electrons and why do conductors have free electrons. It will be very clear when we do that particular topic. Okay, here we have this body is an uncharged body, but mind you, it's a conductor. Here I have a charged body. All right, this is the body which will induce. Now, what is the process of induction? Let's see it. Now, since this body is positively charged, this will attract electrons from, like the entire body here. Since this is a conductor, it has so many free electrons in it. So these free electrons are attracted towards this one. Let's say this end becomes negatively charged because of the movement of electrons. So when these electrons move this way, like the atoms, the particles over here will lose electron, and there they will have less number of electrons in them, meaning they will have positive charges left out there. All right, mind you, if one electron migrates towards this side, then it will leave a proton there. So it means equal number of charge separation happens here. These are called the free induced, all right, because they can move around. They can, if you have anything, you can, if you want to conduct them, they can easily pass over. But then if you see these particular electrons over here, then these are bound. They are fixed. They are fixed induced. All right. All right. This is a process of induction. So in an induction, what happened is the charge separation happened. Here the electrons migrated towards the side and the proton are left over there on the other side. Well, the same thing, what happens in dielectric? Let's see, this is a dielectric now. Now in a dielectric, what happens is we don't have free electrons, so it means electrons cannot migrate here. But what happens there is these atoms which are there in these atoms, this positive charge will attract the negative charges in this atom slightly towards this side, and the protons, the slight positive charge will be left on the other side because it will be pulled, it will be pushed, repelled. So negative charge of the atom will be, like oriented in this fashion, whereas the positive charge will be oriented the other way around, like that. So we will have this. If you look at this, then all the positive charges will be oriented on the other side, whereas the negative will be oriented to the left of it. So this happens, and this particular phenomena of, like the atoms where the positive and the negative charges separates itself without the actual movement of the particles, otherwise no even movement of free electrons are involved there, this phenomena is actually called polarization. So this is dielectric polarization. Okay, so I'm going to stop here about the topic called as induction. This is induction. So induction phenomena is responsible in order to make a body charged, but what I can see over here is the body is not charged simply here, but the charge separation happens. So if you want to connect this one to say earth, all right, then this earth, from the earth, what will happen is electrons can migrate up there, they can neutralize this free induced positive charges, and there, this charges can be neutralized, whereas if I simply remove this positive inducing body from here, then this negative charges will actually go and spread over there, and then this body becomes negatively charged. So that is how I can charge a body with the help of induction. So there are two methods by which I can charge a body. Number one would be with the mode of friction, and the second one would be the mode of induction. Okay, well, let me skip my topic straight up to the next chapter. This is all about introduction in the first chapter. If you happen me to proceed on with the first chapter, then you can actually have my Facebook number, which is 96 350-20422. So you get me on this number and you can suggest me. So what I'll have is, like I'll see the majority of suggestion and I'll come across with that in next class to come. Okay, today I'm going to push myself up straight to the second chapter, and that is the chapter of electric intensity and potential. Well, I'm going to begin first with Coulombs Law. Coulombs Law states that any two charges, let's say there's a charge Q1 and there is another charge Q2. Any two charges attract or repel each other with a force which is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Let's have a see. What do you mean by that one? Let's see this. This is the, like the line which is joining these two charges, and let's say r hat is a unit vector. Conventionally, I can take anywhere this r hat. I can take this direction, otherwise that direction. That is my wish or your wish, what I mean to say. So let's say my origin is taken there, and then I'm taking my r hat in that direction. Let's say the distance between this Q1 and Q2 is r. Then Coulombs Law says that the force of attraction or repulsion between them will actually be equal to, here it is 1 by k, and then this is Q1 Q2 divided by r square. Here you have it. This 1 by k is actually a constant. This is a proportional constant. I will try and understand this one. What actually this 1 by k stand for? This depends upon the nature of units you have chosen and the type of material you are considering. So based on that one, the values of this 1 by k differ. Alright, this is force. If I give a vectorial notation for this one, then it's going to be something like this. Let's say the force on the charge 2 due to 1, that is F21, is going to be equal to, it is Q1 Q2, this is 1 by k of course, divided by an r square, and I can direct it like that. Is that okay? Well, that is, say, the force on charge 2 due to charge 1, it is r hat over there, so this is the idea. Whereas, if I see the other one, that is force on 1 because of 2, on the other hand, will be given as 1 by k Q1 Q2 divided by r square, and this time, let us replace this one as minus an r hat, because I've already considered r hat to be directed that way, so the force on this one, see, is going to be something like this. This is F12, and that is going to be F121. That's the idea. Now, depending upon if the charge happens to be negative, then I will replace this Q1 by minus Q1, or Q2, if Q2 is negative, then replace by minus Q2, and so on and on. Alright. Now, what I wanted to tell you here is, though I have taken the vectorial notation for F12, and if I go and have a see what is F12 here is minus of 1 by k Q1 Q2, well, this can be written this way otherwise. And that is equal to minus of f of 21. Well, so f12 is equal to minus of f21. Though I have taken a vectorial approach of this, but I suggest you that whenever you deal with numerical problems or anything like that based on this force or even intensity, then consider direction. Direction is much more better compared to the vectorial approach in that case. Is that okay? Alright, we will push next to the topic called intensity. Alright. Now, what's the concept of intensity? Well, before I come to intensity, otherwise potential, there are two aspects called intensity and potential. Now, these intensity and potential are the two attributes or two physical features with the help of which I can describe the electric field. Now, say, if I have a charge, if I have a positive charge, let's say, posted somewhere here, so I have a positive charge here, let's say. Now, if there is this positive charge, then it is in the region surrounding this positive charge. If I bring some other charge, let's say, this is, let's say, plus Q charge. And if I bring some other charge, let's say, a plus a small q charge, let's say. Now, if I bring this plus small q charge over here in the vicinity, otherwise close to this plus q charge, then obviously this plus q charge will start feeling the effect of that plus q, capital Q charge. Alright? But if suppose say, I'm not talking about this plus q charge, and this space was vacant initially, alright, and not the board space, I can say this space was vacant initially. Now then, suppose I bring this plus capital Q charge from from somewhere, let's say originated and bring it over here, then this particular plus capital Q charge will feel no influence of any other, because no other charges are present there. But for this particular plus Q charge, it will feel the effect of this plus capital Q charge. Are you understanding with this? This particular plus Q charge, all right, will have an area or the reason, all right, where its dominance can be felt, where its influence can be felt. So that particular reason surrounding it generally is referred to as the field of that particular charge. Though strictly speaking, field is something different when I'm talking about intensity. I'll talk about that next. All right, well anyways, let me bring you the idea of this particular field in some other aspect. All right, this same particular kind of force we also have, right, in a force called, these are generally named as inverse square forces. You see the gravitational forces, capital G, M1, M2 divided by R square. Look at that, they have a similarity. These two forces has a similarity between them. Check this, all right, so called as inverse square forces. Okay, here and there, that particular force is a gravitational force. Okay, so when I go to gravitational force, exactly here I can feel this idea about this one. Suppose this is my charge and some alien body, let's say, all right, try to enter or comes very close to the earth. Then what actually this alien body will do is like, all right, when it enters some region inside, then it will feel like, something is present there. Oh, what is that? And one will feel that here, there is earth. But had that earth been not there, then this alien body would easily drop anywhere without the influence of any other thing. But since this earth is present here, this particular alien body, it's like enters a region, then it will feel another, like added drag because of this earth present here. Earth will actually attract anybody. Say, take for instance you, okay, you are here, all right, on the surface of the earth, you're okay. Suppose you want to go away from the surface of the earth, you jump, let's say, what will happen? You keep on jumping. No, you don't keep on jumping. What will happen there? Earth will drag you downward. You see, earth, all right, earth will keep on dragging you until you reach a particular point. But some point, let's say, if you are, say, projected, otherwise if you jump with a velocity, let's say 11.2 kilometers per, all right, second, then what will happen? Earth will never pull you back. You know why? Because you will shoot in that region where the earth influence will no more be there, and then you will up there in the space, earth's influence won't be there. So that means the field of the earth has, like certain region from where to which it can extend. All right, beyond that, it is not there. Exactly, that's the idea for this positive charge we have there. So in this region, we have the field where the influence of that charge can be felt. If this plus charge enters here, all right, it will feel the interaction, it will feel the pull or the push of this one. If it is not there, somewhere here, then it will nowhere feel it. Not exactly, I won't say here, because if I really say, then this force actually decreases in this fashion. It keeps on going, but it will never be equal to zero, like that. It keeps on going, all right, drops down in the form of inversely as r square. Okay, so that's like E, and then I would say r square. But the presentation comes different here, all right. We're talking about where this distance, well, this we will deal when I talk about another topic, especially conductors and the electric field inside the conductor, due to the conductor and so on. Well, anyways, this is the rough idea about how field, all right, otherwise the force, let me more say the force, and it varies with r, not in r square, but in r. Here we go. Okay. Well, that's the concept of the field. Now, in order to describe this field, all right, there are two physical quantities. One we call it as intensity, another which we call as potential. Let's talk about intensity. What is intensity? Now, intensity at a point in an electric field is defined as the force experienced by a unit positive charge placed at that point. Now, what do you mean by that? Let's see this. Talk about this plus Q charge once again here, all right. And then if you talk about a point over here, let's say this point is A. All right, it is at a distance, let's say r, from this plus Q charge, all right, where I will fix an origin, all right. So my r hat is directed that way. Let's say this r happens to be the position, all right, vector happens to be the position vector of A, let's say. Now, if you want to find out what is the intensity here, then what you do is you bring a +1 charge here, and find out what is the force experienced by this +1 charge. Whatever is the force experienced by that +1 charge, that will be called as intensity at that point. Electric intensity, otherwise very loosely also called as field at that point. Let's have a see. So according to Coulombs law, the force of attraction or repulsion between this here, between this +q charge and this +1 charge here will be equal to, let's have a see there. What is it? It will be equal to F, all right, and here it is termed as E, the electric intensity, field, otherwise field intensity or electric intensity or simply intensity, E will be equal to Q and then 1 divided by an R square with of course that constant. I will talk about this constant very quickly now in a brief. Let's see what do you mean by that. There you go. That is the intensity at that point. Now vectorially, let's have a see vectorial idea of that one. We all know that like charges, they repel each other, and unlike charges, they attract each other. So if I have a +q charge over here and there is a +1 charge here, then obviously the force here is going to be repulsive. So here the force on that unit positive charge E, which we call as intensity, will be directed that way. It will be directed from O to A. So directed along OA precisely. Otherwise vectorially I can write that one as this is like Q by K R square with R hat. There you see, that's the intensity at that point. All right, let's talk about this K thing very quickly. Okay, so that constant 1 by K, we'll see what is that. F is equal to 1 by K. Give me a break, I'll come back to that intensity very quickly. Let me tell you about this constant because it's so important over here. All right, so 1 by K, Q1, Q2 divided by an R square. Let's see this 1 by K. 1 by K basically, all right, it depends upon the unit chosen, all right. So if I'm going to talk about if, all right, in SI unit if I'm going to express, and in air, listen very carefully, SI unit and in air or vacuum, F is going to be 1 by 4 pi epsilon naught and Q1, Q2 divided by an R square. So this 1 by K takes the form of 1 by 4 pi epsilon naught, where this epsilon naught is actually called permittivity of free space. Permittivity of free space. All right, the value of epsilon naught comes out to be 8.854 into 10 to the power minus 12. Unit of this one is supposed to be, have a C, unit of this one I'm looking for. Epsilon naught here, Q1, Q2 divided by F with an R square. So it's like Coulomb square per Newton per meter square. So this is the value of epsilon naught. And actually, how did I get this? Then I can go straight up to this one. It is like 1 by 4 pi epsilon naught has a value of 9 into 10 to the power of 9. 1 by 4 pi epsilon naught has a value of 9 into 10 to the power of 9. Unit of that one, Newton meter square per Coulomb square. Newton meter square per Coulomb square. That is the value of 1 by 4 pi. Now if you push on with this one, like what is epsilon naught, or they bring this 9 into 10 to the power 9 down here and find out what is that epsilon naught, then you will exactly get this epsilon. What is this epsilon naught? As I told you, it is permittivity of free space. What is permittivity? Now permittivity is an electric character of a material. It is the electric character of the material I'm trying to tell you, all right, which you will study when you do the chapter called electromagnetism, especially in the chapter of electromagnetism. When you see the velocity of light in air or vacuum, then it is given by 1 by square root of epsilon naught and a mu naught. This epsilon naught happens to be the electrical character called as permittivity of the free space, whereas mu naught is called permeability. Now that's the magnetic property of the matter, well, which will be discussed later. Well, there you go. So this is the case of in SI unit and in air. SI unit and in air. Is that okay? All right. Now, in SI unit and in any other medium, what happens? Let's see. Now that is F will be equal to 1 by 4 pi epsilon Now this epsilon is called permittivity of that particular medium. Alright, 1 by 4 pi epsilon called as absolute permittivity, and then that is Q1 Q2 divided by n r square. That is in a SI unit and in a medium. In a medium whose permittivity is epsilon. Now let's find out what is that actually. Now generally, if I look at something called as epsilon r, it is called relative permittivity. Relative permittivity of a medium is actually given by an epsilon naught. And in most of the cases, relative permittivity comes out to be something called as K. Now this K is called dielectric constant, dielectric constant of a medium K, and that is equal to epsilon naught, and that is epsilon by an epsilon naught. Here you go. So what is epsilon then? So epsilon will be equal to epsilon r epsilon naught, and that will be equal to K epsilon naught. So if I bring it over here then that F now becomes, this F now becomes, F will be equal to 1 by 4 pi epsilon naught with a K, and then Q1 Q2 divided by an r square. There you go. From here you can even find out what is the concept of this K, dielectric constant. It comes out to be the ratio of the field. Alright, here if you see this, what is K? Then here this one is actually, if I call this one as F1, let's say for the time being, F1, then F1 will be equal to F by K. The F is in free space. F is Q1 Q2 divided by 4 pi epsilon naught without this K, and then r square. Alright, so K is hanging down there. So what is K then? So K is equal to F by an F1. Here you go. Alright, so what is K? K is the ratio of the fill between, alright, any two charges in vacuum to that in the medium. Now K is actually called dielectric constant. Dielectrics generally called as what? They are called as insulators. Okay then, well, what happens in CGS unit? Let's have a see. The same thing in CGS unit. Now in CGS unit and in air. In CGS unit and in air, in CGS and in air, 1 by K happens to be 1. It means K is equal to 1. Capital K there is equal to 1. So your F will be equal to Q1 Q2 divided by an r square. Whereas in CGS and in medium, other than air or vacuum, then this particular K, capital K, happens to be the small k called as dielectric constant. Same thing, that same dielectric constant here, and then your F will be equal to Q1 Q2 divided by K with an r square. Here we go. So these are, well, you don't need this force idea here because you don't place on the other side that particular idea about here also. So I have to bring it an r hat over here to tell it precisely that that is a vector over here, because once I represent this as a vector form here, I cannot leave it alone like that without representing with an r hat. R hat is actually the unit vector, all right, along r. Well, basically that much I would say about force, and in the different system of units we have rightly seen what this Coulombs law can take forms of. Going back to intensity, alright, we just got the idea about intensity, that intensity is the force experienced by unit positive charge. Now unit positive in idea is just taken as a standard. The intensity is the force experienced by unit positive charge placed at that point. Okay, now the next thing which describes the field, alright, will be potential, electric potential. Now let me describe electric potential to some extent. Now what is the concept of electric potential? Bring it here. I know it describes the field, but let me talk about electric potential to some details. Let's say, now if you want to talk about the transfer of heat, otherwise flow of heat from one body to another, if they are in thermal contact with each other. Let's say the body A and a body B are in thermal contact with each other. This is body A and the body B. They are in thermal contact with each other, let's say. Alright? Then the flow of heat from body A to body B or body B to A will depend upon one particular factor, and I hope you people know it, and that is temperature. So temperature is that particular physical quantity which decides the flow of heat from one body to another when they are in thermal contact with each other. Exactly in the similar manner, suppose say any two bodies, say hydrostatics I'm talking about, any two bodies, otherwise cylinders, alright, are connected to each other and they have, you know, like liquid, otherwise say water in them. Alright, once, you know, the connection between these two is opened, alright, then if the water flow starts, then the flow of this water will depend upon the factor called as level of water. So it is the level of water which decides the flow of water from one body to another in a connected system. Exactly in the similar manner, we have one particular topic called as potential. Potential is that particular character which decides the flow of charge. Alright, charges flow from a body at a higher potential to the body at a lower potential. Alright, but then in particular context of potential, since we are talking static electricity rather than the current electricity where the motion of charges are involved, so that's the reason why I will bring in another definition of potential. What actually is potential? The alternative definition of potential. Let's see. So I know that this reason here is the reason where the influence of this particular positive charge, let's say any charge can be felt. So this region happens to be loosely filled of that particular charge plus Q. Alright, now let's take 2 points over here. One point here and another point here. Alright, so if I talk about a point A and another point B here, now these particular points will develop a kind of character that if I have to move any other charge, let's say plus Q, small letter Q charge, from this point to that point, then, alright, strictly speaking, this particular work which is to be done here, it is independent of the path chosen. It means like I can take it this way, I can take that way, I can take this way, I can go all around here and bring it over here. So it's absolutely independent of the path chosen. The work done will exactly come out to be same no matter whichever path you follow, like path 1, path 2, path 3 and path 4 if you go. But then the W1 will come out to be same, W2, W3 and W4 will all come out to be same. And what is that? That is actually equal to VB minus a VA, VB minus a VA, VB minus a VA and so on and on. What is this V then? This V is actually called potential at that point. Now what is potential? Okay, let's bring in more then. So if you want to find out what is the potential at a point, alright, then the potential at a point, let's say this any point, let's say I have any point P over here. So if you want to find out what is the potential at a point P, alright, due to this particular charge plus Q here, mind you, in absence of this plus Q charge, there is no potential. There is no field, there is no intensity, and there is no potential. But if there is this plus Q charge, then in the surrounding region of this plus Q charge, there will be field, and because of that, there will be intensity and there will be electric potential. Now let's see what is the potential at a point P described as. Okay, it is said as the potential at a point P is defined as the amount of work done to bring a unipositive charge from infinity to that point P. So whatever the work I do to bring this unipositive charge from infinity to that point P, that amount of work done, okay, suppose that I do the work W to bring this unipositive charge from infinity to this point P, then this W will be said as potential at the point P. So the potential at the point P, if I say V, then V is actually that W thing. Okay, so it is defined as the amount of work. So why infinity? Why is that taken as infinity? See, infinity, see, we believe that at infinity, the potential due to this point, otherwise field due to this point is practically null, zero. There is zero potential at infinity. See, we all had that one, that F is equal to, you know, like inverse square is proportional to inverse square. So if R happens to be infinity, then F comes out to be 0. Otherwise, E comes out to be 0. So the field force, all right, all are 0 at infinity. So it means this particular charge has no influence at infinity. That's the reason why we generally take that one as a standard. All right. In case of gravitation, we all know the surface of the ground, all right, surface of the earth is taken as that standard, and all the heights above the surface are taken to be h, and where the potentials are described with reference to that one. Okay, that one you have already done in class 11. All right, here we go then. So that is the potential. What about, all right, potential difference between any 2 points? Okay, potential difference between any 2 points, all right, is defined. Suppose I have 2 points over here. Let's go back to this A and B otherwise. So the potential difference between these 2 points, A and B, otherwise VP minus VA. What is that? The potential difference between any 2 points is defined as the amount of work done in moving a unit positive charge from one point to another. I think these are the basic definitions which we have in class 10. We've already done it. Let's go to the class 12 version then. What do we do in class 12? Let's see. Okay then. So I want to find out what is the potential at the point P. All right. Possibly, I think that's going to take some time, and I think we will be done for today, or might be one more topic to go after that. Let's see. So potential at a point P. I want to find out. Here we go. So here is a plus Q charge. These are point charges, mind you, just I'm taking a bigger structure, but that's a tiny one. They are called as point charges. Okay, so let's say this is taken as an origin. Find out here, this is a point, all right, let's say A, and somewhere here is the point B. Okay, we all know the field at A. So say that OA is equal to R, let's say. OA is equal to R, and let's say R hat is a unit vector, all right, directed from O to A. O is taken as origin. The field at A is described as E, and it is given as E will be equal to, take the SI unit thing, 1 by 4 pi epsilon naught with a capital Q by n R square. Here we go. That's the field. Let me bring in that R hat thing over here. So that is the field at the point A. Now why I am bringing this field idea? Because I'm trying to find out what is the work done. See, this derivation is potential at a point, all right, in an electric field. That's the derivation we are doing. Okay, so I want to find out what is the potential at the point A. So what I found here first is what is the field at A. I'm just finding out that one first. Okay, now what will I do here is I will think of this particular distance from A to B as, let's say, dr. All right, that is a tiny incremental distance. I'll give the reason why I'm taking this incremental distance dr. Okay, so I have to find out, let's say I have a +1 charge here, all right, and I'm trying to move this +1 charge from A to B. Okay, so in doing so, work done will be equal to, let's write it, work done to move +1 charge from A to B, all right, AB is equal to dr, let's say, the scalar part of it. Then the work done dW will be given by E with a dr vector, let's say. So this work done is given by E dot dr. Why E? Because E is the field there, and field is the force on a unit charge. That's the reason why I'm taking that unit charge over here. All right, so E dot dr, and that comes out to be, this will be equal to 1 by 4 pi epsilon naught with a Q by an R hat dot dr. That's the case if I do it properly. Then that is equal to 1 by 4 pi epsilon naught with an dr, all right, R is square down here, and here will be equal to a minus there. Have a seat. So dr, why is that? You see this R hat and a dr are opposite to each other, and this is the dot product. A dot B is AB cos theta, and the angle between R hat and a dr, because I'm moving this way, the angle between them happens to be 180 degree, and cos 180 is -1. That's the reason why we have a minus over there. So that is the work done, all right, to move a charge, a unit positive charge from A to B. Okay, so therefore the potential at, all right, the point B, or otherwise A, I would say, that is the work done, all right, to move +1 charge from infinity to which point? A. So, have a see here. According to the definition of potential at A, it is the work done to move unit positive charge, that is +1 charge, from infinity to that point. So I'm moving unit positive charge from infinity to this point, alright, and that is the potential at the point A, alright, and what is that? That is the total work done. So I'm going to find out this total work done as integration of dW. So I'm going to integrate this tiny work done. Why I have taken this tiny work done over here, taken as from here A to B, mind you this dr is so tiny, so incremental. I'm going to find out what is that work done here. So in the process from moving from infinity to this point, I'm taking this tiny work done, dw1, dw2, dw3, so all these tiny work done I'm taking and I'm integrating that one to find out the total work done. Alright, now why is that? Why is the necessity of taking that tiny work done only for a small distance dr? Mind you people, this particular intensity depends on r. So farther you are away, alright, it depends on the value r. So E will take different values at different distances, at different points. So but for this tiny incremental distance dr, we are assuming as if this f remains constant. It is not changing. And so I am taking that, alright, E dot dr as the tiny work done here. Otherwise, here also I would be going for an integration part, because we know just for that tiny displacement dr, we are assuming as if E is not changing. So here we go. W is equal to integration of dw, and that is equal to integration minus of integration of 1 by 4 pi epsilon naught with a q by an r square, and then that dr thing is there, and this is infinity to that particular point, and this particular point A has a position of r from infinity to r. See the total work done to move unit positive charge from infinity to the point r. That's the idea of integration. And here I go, that's equal to minus 1 by 4 pi epsilon naught. Alright, and there is q, I'll bring q here, alright, and that is integration of dr by an r square infinity to r, and that will come out to be, that is equal to minus q by 4 pi epsilon naught. And then here we go, this is like minus 1 by r, and the limit will be infinity to r. Here we go this, so this w then will be equal to here minus q by 4 pi epsilon naught, and limit here will be taken as minus 1 by r, and then there is a minus becomes a plus for the other one, and that happens to be 0, and this is equal to q divided by 4 pi epsilon naught then r. That is the potential at the point A, 4 pi epsilon naught then r. There we go. Mind you, this potential is a scalar. Potential is a scalar. Intensity is a vector. Potential is a scalar. But then what kind of a scalar? Mind you, potential is a signed scalar. We all know work done. Work done by the field is taken to be negative, and work done by the external agent is taken to be positive. Mind you, so this potential, when I speak about potential can be negative, potential can be positive. Is that okay? Let me finish this session just by discussing that particular point. Very quickly I'm going to discuss and finish it over here. Let's have a see. Suppose I have a positive charge over here, plus q charge. I talk about a point here, A. Now whether the potential at A will be positive or negative, let's have a say. So to bring a +1 charge, who does the work? Let's have a say, who does the work? This plus q charge will repel this +1 charge. So since it is being repelled, the field do not do the work, because field is directed that way. So who have to do the work? External agent must do the work. Now since the external agent must do the work to bring this +1 charge from infinity to this point A, the potential at A is positive. But if I say on the other hand, I have a minus q charge here and this same point A, and I am trying to bring +1 charge from infinity. So now here, who does the work? See, minus q charge will attract that +1 charge. So who does the work? Field does the work. And that's the reason why, since field is doing the work, it is negative. So VA here is negative. So we just got an idea that the potential due to a positive charge is positive and the potential due to a negative charge is negative. Hope I have made some flaws and mistakes in between in order to put the right things in the like right order, because we all know that this is for the first time we are coming up with in classes like this. Hopefully in the next classes we're going to come up more organized. Thank you very much.